Hello, my name is Josh. I'm a computer science student at UCCS. This presentation covers the basics of an ANOVA test and how to perform that test using SPSS software. Alright, so the overall layout of this presentation will first cover the basic features of an ANOVA test, introduction to using SPSS software, showcasing the provided cybersecurity dataset, and finally performing the ANOVA test on that dataset. Alright, so ANOVA, or analysis of variance, is a statistical method used to determine whether there is a significant difference between the means of three or more groups. It's especially useful when we have multiple data sets and need to check to see if at least one of them is significantly different from the others. For example, if we're testing student performance across different schools, ANOVA would help us see the differences in average scores are just random variations or if they actually mean something statistically. ANOVA works by comparing the variability within each group of the variability between groups. If the variation between groups is much larger than the variation within its groups, it suggests that at least one group's mean is significantly different from the others. But if the variations are similar, we can't confidentially say that any group stands out. A key output to ANOVA is the p-value, which tells us whether differences are statistically insignificant or just due to chance. Let's say we're testing three antivirus programs. We have program A, B, and C, and we want to see which one consumes the most CPU resources. We collect CPU usage data while running each of the program and then apply ANOVA. If the results show significant difference, we can conclude that at least one program is more resource intensive than the others. This kind of analysis is crucial in cybersecurity and IT because it helps optimize software performance, ensuring that programs don't slow down computers unnecessarily. Okay, so ANOVA, why? One of the biggest advantages of ANOVA is that it allows us to compare multiple groups at once, avoiding the need for multiple t-tests. If we were to compare three or more groups using individual t-tests, we would increase the risk of making a type 1 error, that is, falsely finding a difference when none exists. ANOVA eliminates the issue by analyzing all groups simultaneously, ensuring a more accurate and reliable result. ANOVA is powerful because it helps us detect patterns in our data. Instead of just knowing whether values differ, we can understand why they differ. For example, if we're analyzing cybersecurity attack patterns, ANOVA could help us determine whether the size of the data packet influences the type of attack being used. This insight allows us to take action based on meaningful patterns rather than random fluctuations. ANOVA is widely used in decision-making across different fields. In business, it helps companies determine whether marketing strategies lead to the highest sales. In medicine, it can analyze the effectiveness of different treatments for a disease. In cybersecurity, it can compare the impact of different security measures on preventing attacks. By using ANOVA, we can ensure that our decisions are based on data-driven. So before we go any further, let's use some real-world examples to kind of get a better idea of what exactly we're doing here. So for in medical research, ANOVA is frequently used to compare the effectiveness of different treatments. For example, if we have three different medications for treating high blood pressure, ANOVA will help us determine whether one drug is significantly more effective than the other in lowering blood pressure levels. This is crucial for evidence-based medicine, ensuring that patients receive the best possible treatment based on statistical analysis rather than just observations. In business, companies often test different marketing strategies to see which one drives the most sales. Suppose a company runs three separate advertising campaigns, one on social media, one through email, and one on TV. Instead of running multiple t-tests, which would increase error rates, ANOVA helps determine whether any of these strategies significantly outperform the others. This allows businesses to invest their marketing budget wisely and focus on the most effective strategies. Manufacturing companies rely on consistency in their production lines, but sometimes machines in different locations may produce varying results. ANOVA can be used to check whether defect rates differ significantly between machines in different factories. If one machine has a higher defect rate, it might need maintenance or calibration. This kind of analysis helps manufacturers maintain quality control, reduce waste, and optimize production effectively. Okay, so when we do ANOVA testing on SPSS, we're going to be given two different tables. The first one is going to be giving us different values and variables and all sorts of good stuff. So let's go ahead and figure out what exactly we're looking at here. So the first thing is going to be sum of squares. The sum of squares measures the total variation in the dependent variable, showing how much data points deviate from the mean. A higher sum of squares suggests greater variability, meaning the data points are more spread out. The next thing is degrees of freedom, or DF. Degrees of freedom represent the number of independent values that can vary while still satisfying certain constraints. It helps determine the reliability of statistical estimates, with higher degrees of freedom generally leading to more stable results. The next thing is mean square, or MS. The mean square is calculated by dividing the sum of squares by the corresponding degrees of freedom. Providing an estimate of variance, it helps compare variation between groups versus variation between groups to determine statistical significance. Followed by the F ratio, or F statistic. The F statistic is used to determine if the group mean is significantly different from each other by comparing the variance between groups to the variance within the groups. A higher F value indicates stronger evidence that at least one group mean is different. The last thing is going to be the significance. It's going to be sig or the p-value. The p-value tells us the differences observed in the data are statistically significant or likely due to chance. If the p-value is less than 0.05, we reject the null hypothesis and conclude that at least one group differs significantly from the others. Okay, so the second table is going to be effect sizes. Now, effect sizes measure the strength of the relationship between the independent variable, or the factor, and the dependent variables, or dependents. These values will help you understand the practical significance of your findings beyond just statistical significance, or the p-values. So the first thing is eta squared, is a measure of the effect size that allows us to know how much of the total variance in the dependent variable is explained by the independent variable, or the factor. The next thing is epsilon squared, which is an adjusted measure of the effect size that accounts for violations of the assumption. It often used when the data does not meet the assumption of equal variances across groups. Omega squared is another measure of effect size that is more conservative than eta squared and adjusts for sample size. It tries to estimate the proportion of variance if the dependent variable that is explained by the independent variable while accounting for other factors like sample size. Confidence interval will be over everything and is the range of possible values for the effect size, kind of giving more of a sense of precision. Okay, before we go further, let's go ahead and just talk a little bit about what exactly SPSS is. So SPSS, or Statistical Package for the Social Sciences, was originally developed in 1968 and is now owned by IBM. Over the decades, it has become one of the most widely used tools for statistical analysis across various fields. Its longevity and continued updates make it a reliable choice for data analysis. SPSS is widely used by professionals in different industries. Scientists and researchers use it for conducting experiments and analyzing trends in large data sets. Business analysts rely on it to uncover patterns in sales and customer behavior. Even marketers use it to measure the effectiveness of advertising campaigns and consumer preferences. Its versatility makes it a powerful tool for anyone dealing with data-driven decision-making. One of the key advantages of SPSS is that it covers the entire analysis process. You can use it to design surveys or experiments, collect and organize data, run statistical tests, and generate detailed reports. This makes it an all-in-one solution, reducing the need to switch between different software tools. Now, at first glance, SPSS might remind you of Microsoft Excel because of its spreadsheet-like interface. But the key difference that makes SPSS is that it's built for statistical analysis. It comes with built-in functions for running complex tests like ANOVA, regression analysis, and predictive modeling, things that require extensive formulas and manual work in Excel. This makes SPSS a more efficient and accurate tool for handling statistical data. Okay, so now that we covered all that information, let's put it in action. First off, we're going to cover some of the basic features of SPSS, and then I'm going to plug in an easy to understand data set, And finally, we use an even bigger data set to perform the ANOVA test.
Using a giant data set, let's just use something simple that we made. So looking at this data set, we have something simple. We got names, age, hours of sleep, favorite color, daily caffeine intake, and when they do exercise, how many hours do they exercise? By the way, I just want to point out all these are randomly generated, so I wouldn't be surprised if the ANOVA testing that we get out of it really doesn't make much sense. But this is just something easy to wrap your head around on what exactly we're doing before we go into a bigger data set. So looking here, it looks like the youngest age I think is 18 and the oldest is 42. So when we do an ANOVA testing, it's going to break everything down by age groups. And this is what we're going to use as our factor. Hours of sleep. Well, it looks like the youngest one is probably, I think there's a 4.5 in here. And then also we have something sitting around 7.5. Favorite color is also in there, but it really has no significance whatsoever when it comes to using the ANOVA testing. I just have this in there to show something else with a different feature. Caffeine intake, what we're trying to do is also going to be one of our dependent variables going against the age. The smallest one I think is 100, the biggest is a 400, which is very unhealthy. Exercise hours, we have people like Alice just tanking it out with 4 hours of working out, and then we got some people with 0. So let's go ahead and plug this thing in SPSS and see what we can do with it. So I already got it pulled up right here. And it's pretty easy in SPSS. All you got to do is go to File, Import Data in Excel, and then you just pull it in right here. So as you can see in here, we have a couple different things we can look at. At the top, it has what kind of data set it is, or excuse me, what kind of variable it is, and what can we do with it. If it has a little ruler next to it, like these guys, it means that we can scale it and we can do something with it. If it has the 3 little circles, that means it's nominal, like this, excuse me. So we'll go over to variable view. Nominal means that everything that's in it all have the same exact value, which would make sense. I mean, obviously a bunch of names, and nobody has a higher priority in name unless you wanted to break it down by alphabetical order or something like that. But we can do that. So let's go back to the favorite color because we want to look at something like that. So let's say that we want to put all of these different colors and we want to have some scalable value with it. We can do that. So what we'll do is we'll go to transform. I want to go to automatic recode, favorite color, put it in. And let's just say we want to call it, I don't know, favorite color num, right? I want to add that. I'm going to hit OK. Bam! And now it's going to generate all these different numbers. It looks like I typed in purple wrong somewhere. But it's going to generate all these different codes attached to the color. So B is a shorter in the alphabet, so it's going to be number 1. And yellow, Y, is towards the end of the alphabet, so it's going to be the highest number. So it doesn't really matter right here, but in our next data set, it's actually going to be important. We're going to have to adjust that before we do something like this if we're actually going to get the full value out of it. But anyway, so let's go and close out of this. And we can look at our data set again. Now we have all these different color codes attached to our names. So Alice over here, blue, is now 1. And once again, blue is 1 with Ian, right? Either way. And then you can go back to favorite colors and you can change this guy to scale. Jeez, come on. There we go. I could change it to scale and now I can actually do something with it. But we're not going to do that. I just wanted to show you guys how exactly you can change, manipulate data. And you can even go in here. So let's say I want to go to values and I can adjust it right here if I wanted to as well. So let's go back to data view and we're going to go ahead and try an ANOVA testing with these guys first, just to show some basic input that we get, what it means, what it does, and then we'll go into a bigger data set. So let's go ahead and we're going to go to analyze, compare means proportions, and we're going to hit the one-way ANOVA. All right. So remember, the factor we want to use is the age. So I'm going to go ahead and drag that guy over here. And then I'm going to use hours of sleep, caffeine intake, and exercise hours as our dependent list, right? So these guys, favorite color, he stays out. I don't care about him. Okay, boom. All right, so here we go. Here we got the ANOVA settings, and then we're going to read a couple things here on what exactly we're looking at here and what it means. So our factor, remember, is the age. Well, we're grouping in our data set by age. For instance, if you segment the age ranges like 18-25, 26-35, 36-45, well, you're organizing your data into categories based on groupings. Each range becomes a group in your analysis. Your dependent variables, like hours of sleep, caffeine intake, and exercise hours, well, these variables are being measured or compared across the different age groups. So we're essentially asking, do these dependent variables differ significantly between the age groups? So what does this mean? Well, when we did the ANOVA, we're checking to see if the age affects the dependent variables. For example, does the average caffeine intake vary across age groups? Do people in their 20s exercise more than people in their 30s or 40s? And is there a difference in the average hours of sleep based on age? So when we do an ANOVA test, it tells whether the means or the dependent variable differs significantly between the age groups. If there is a significant difference, it suggests that the age might influence those variables. So the first thing we're going to look at is we're going to look at hours of sleep, and then we're going to look at between groups and sum of squares. So this is a variability of the hours of sleep explained by the factor of age groups. It's relatively high compared to within the groups. And then we have a total adding them up. The next thing we're looking at is going to be the degrees of freedom, which is 22. Remember, degrees of freedom are numbers of groups minus 1. And then within groups is 3. The mean square is going to be 1.067, and within groups is 0.575. And the F statistic is 1.856. Excuse me. And this compares between groups of variability to within groups of variability. So the higher the F value, the more likely the difference between the groups are significant. And then looking at this, the most important is significance, or the p-value, is 0.339. So since the p is greater than 0.05, this means the differences of the hours of sleep across the age groups are not statistically significant. So this suggests that age doesn't strongly affect hours of sleep in that data set. So we can look at these other guys too. So, we got caffeine intake, between groups, within groups total. Wow, look at that number. But obviously these are all randomly generated numbers, so this isn't really accurate data. I'm just showing you guys what exactly we're looking at. The degrees of freedom is going to be the exact same because we have the same exact amount of people that we're testing against, which is 23 people total, so 23 minus 1. And we have different things that we're testing against. We have the mean square, once again, the caffeine intake. So whoever's that one person that had 400 milligrams of caffeine and the other person only had 100 is what's really screwing this whole thing up. And then our significant value. So since it's greater than 0.05, there's no statistic value of this and it's not randomized. Looking at exercise hours, same exact thing. It's a little bit more of a normal numbers that we would get, just like the hours of sleep. And then same thing with degrees of freedom, the exact same thing, different variables, different names. And then we're looking at the mean square, and then the F statistic, and once again, greater than 0.05, so there's no statistical value, and it's not really randomized. So anyways, that's just a basic means of what we're looking at when we're looking at the first chart. But then let's look at the second one. And what are we looking at? So the first thing, let's look at all these different things. So like I said in the slides, first thing we got is the eta squared, which is a measure of the effect size that shows how much of the total variance in the dependent variable, like hours of sleep, caffeine intake, is explained to the independent variable, in this case, which is age. So our interpretation is, well, the larger the values, this comes a stronger effect. Values close to 0 suggest a small effect, while values closer to 1 indicate a larger effect. So looking at our results, well, our hours of sleep is 0.932, which is also 93.2% of the variance of sleep hours. Caffeine intake, right here, is 95.7% variance, and exercise hours is 90.6% of variance in the exercise hours. The next thing we're going to look at is epsilon squared. And once again, what it is epsilon squared is an adjusted measure of the effect size that accounts for violations of the assumption of security if applicable. It's often used when the data does not meet assumption of equal variances across the groups. So looking at this, our interpretation will be epsilon squared's values are interpreted in a similar way to ETA squared. But they tend to be a bit more conservative, i.e., they tend to provide smaller estimates of effect size. Now we're looking at this as our confidence interval. Well, what is that? Sorry, what it is the lower bound right here is, and the upper bound represent the range which the true effect is likely to fall within 95% confidence. So our interpretation is a narrow range indicates a greater precision in the effect size estimate. A wide range suggests greater uncertainty. And if the interval includes negative results, well, it might indicate that the effect is weaker and not reliable, like we have these guys right here. And so looking at our results, our eta squared and confidence intervals, which is we got some things are coming out at 0.000, and we got a 0.813 somewhere around here. Where'd he go? I think I got confused. I think I'm talking about this guy. Excuse me. Show more uncertainty, but they are mostly positive, indicating a strong effect. So for the omega squared and epsilon squared, the negative values in the lower bounds with the negative values, like this guy right here, this negative 0.733, suggests that there may be irregularities or variability. So in summary, looking at this whole chart that we just did here, excuse me, age seems to explain a larger proportion of the variance in hours of sleep and caffeine intake. So with eta squared values over 90%, however, the confidence intervals for some of the omega squared and epsilon squared values suggest that there could be some issues with the data or variability that needs further inspection. So for exercise hours, while it also seems to explain a significant portion, the effects are somewhat weaker compared to sleep and caffeine. Now we have a giant data set that we're actually going to do a real ANOVA test on. So here I have a list of cybersecurity attacks done by that have been recorded by a cybersecurity product, usually ranging, I think, from 2020 to 2023. And inside of it, I have the timestamp, source IP address of the attacked, the destination of where it is being attacked, source port, desk port, protocol used for the communication, packet length of data transfer, packet type, the traffic type, as well as anomaly scores, which I want to use this as our factor for our ANOVA testing. Alert warnings, alert triggered or not. I mean, honestly, this is a yes or no kind of a thing. More like a Boolean factor. And then we have different attack types, malware, DDoS, and intrusion. And then we have what happened, what did they do? Well, did they log it, block it, or whatever. That's really it. So it's kind of like an option kind of thing. And then our severity level, which we want to use this as well, we have low, medium, and high. And just like I showed you guys with the favorite colors in the previous thing, we're going to have to manipulate this a little bit so we can actually use it as part of our ANOVA testing. By the way, I just want to point out we have 40,000 entries into this bad boy. Okay, so this is not 23 people, this is 43,000, or excuse me, 40,000 different entries of cybersecurity attacks. And we want to do some ANOVA testing on this, right? Okay, so let's go ahead and open up our SPSS. Here we go. Boom. Here it is. Why didn't it open? Come on. Sorry. Why isn't this working? Okay, there it goes. Thank you. Sorry about that. Okay, so we have go ahead and got this thing opened up. Once again, imported it from an Excel spreadsheet. Pretty easy. And looking at it, we already have all these different variables that we can manipulate here and do something with, right? So like I said, the biggest thing we want to work with is our anomaly scores is going to be our factor. And then for our dependent variables, we want to do, I think I want to do packet length. Where's he at? Packet length right here, because we have scalable values. How much data transfer is going between each of these attacks? Let's see. Another thing I would probably want to do is attack type. Here, these are all strings, but I can show you guys how to manipulate that into numbers instead. Now, the attack types all have the same value. It really doesn't matter what it is. It can be 1, 2, or 3. They all have the same exact value for scaling wise. So it doesn't really matter what kind of attack it is, but I do want to put it a part of our ANOVA testing. And then our severity level is also going to be part of this guy. Now, the severity level, we are going to have to manipulate a little bit here, because if you remember right, when we did the favorite color thing in the last example, it's going to, if I automatically turn these guys into numbers, it's going to go by alphabetical. So it's going to make H like 1, and then it's going to put like low like 3, and medium is going to be 2, or not even, excuse me, medium is going to be like 3. I don't even know. But the point is, it's not going to be what we want. What we want is low to be 1, medium 2, and high 3. And that's going to really make it a lot easier to translate what we want to do in our ANOVA testing. So let's go ahead and manipulate some data here. So let's see. I want to transform first. I want to do the easy one. Let's do attack type. So I'm going to transform, and I want to do automatic recode, and I want to go to our attack type. Now, where are you at? There you are. Yes, sir. Put them in, and let's go ahead and call them something simple. Attack type num, right? And I'm going to add them. Okay. Now, what it automatically given our results is it said, okay, DDoS attack is 1, intrusion is 2, malware is 3. I'm cool with that. I agree with it. Works for me. Okay. Like I said, if we go to the variable views and we can look at attack type, it's nominal, and that really makes sense. They're all the same. They're all different attacks. It doesn't really matter what is what. They all have the same value, so that's fine with me. But now that they have numbers, I could put them into the ANOVA setting. But let's go back to data. So the next thing I want to do is severity level. Now, like I said, if I just get ahead and did the automatic, I'm not going to get the numbers that I want. I'm going to have to manipulate this just a little bit more before I do the automatic. So first things first, let's go to transform, and I want to recode same variables, right? So we're going to go to severity level right here, put them in, and I'm going to click old and new values. All right, cool. So I'm going to say, remember we have low, medium, high. So I'm going to say low, and the new value is 1. I'm going to add that. Bam! So it takes care of it. Now the next thing I'm going to put is medium, medium, and I'm going to say that one is going to be 2. Add that in. Last one, high, and I want that one to be 3. I'm going to add it in. Continue. Okay. Bam! All right, cool. Now it transformed all of my different severity levels. Instead of it saying low, now it's a 1, mediums are 2s, and the highs are 3. Now I can really work with that. But let's do one more thing, and then we can start doing ANOVA testing. So then I'm going to go back to transform. I'm going to automatic recode. And I'm going to use, first off, let's get rid of this guy before I mess things up. I'm going to go back to our severity level that we created. Bam. And I'm going to call it severity level num. All right. Add new name. Okay. Beautiful. Okay, now 1 equals 1, 2 equals 2, 3 equals 3. Fantastic. Okay, so now we can actually do our full ANOVA testing with this data set that I want to do and find out more about with the anomaly code. So let's go ahead and go back to analyze, and I want to go to compare means and proportions, one-way ANOVA, and let's put some things in here. So I want anomaly scores to be my factor. I want packet length to be a part of this. I want attack type to be a part of this. And I want severity level to be a part of this. Bam. Let's do this. Okay, let's look at and see what we got underneath the hood. So first things first, let's look at this. So our factor, once again, is the anomaly score. So what we're grouping here is our data set by anomaly score, meaning that you're analyzing whether different anomaly score groupings affect packet length, attack type, and severity level. So the dependent variables, packet length, attack type, and severity level, well, these are the variables being measured or compared across anomaly score groups. The goal is to determine, does packet length vary significantly across different anomaly scores? Is there a difference in attack type distribution based on anomaly scores? And does severity level change significantly with anomaly scores? So, first things first, let's look at our packet length in between groups. Dang, look at that giant number, right? So that represents the variability in packet length explained by anomaly score groups. The within groups, which is even higher, is the variability within anomaly score due to the individual differences, and the total SSs is just all these guys added up. We're going to look at degrees of freedom, which is 9,825, because remember, we're comparing against many different attacks, not just 23 different people like in the last example. And within groups, we have 30,174 remaining variability from same sample size minus the groups. Let's look at the mean square here. This giant number, well, that's SS divided by DF between. And within groups, we have pretty much kind of like a similar number, which once again is the SS divided by the degrees of freedom. Let's look at the F statistic, which is the 1.107. Well, that measures how much larger between the group's variability is compared to within groups variability. And then the most important thing, let's look at the significance thing. So that's the p-value of 0.157. Well, since it's greater than 0.05, the differences in packet lengths across anomaly scores groups are not statistically significant. So this suggests that anomaly score does not strongly affect packet length in this data set. Now let's look at attack type. So same thing, we got a lot of the same numbers here. We got some big numbers going on with the sum of squares. Degrees of freedom, once again, is the exact same because we're comparing against all these other different attacks, like 3,999, because there's 40,000 different entries inside of this data set. The mean square here, though, this one between groups is 0.655 and within groups is 0.673, and the F statistic right here at the 0.974, well, that indicates variability between anomaly score groups relative to individual differences. And once again, let's look at that significance value. Well, it's greater than 0.05. So once again, there's no significant difference in attack type between anomaly score groups, and this suggests that anomaly score does not significantly explain the variance in attack type. Well, going back again with the severity level, remember we had 1 is our low, 2 is our medium, and 3 is our high. Well, between groups, once again, we have these ginormous numbers, and then we have the degrees of freedom is the exact same as the other guys. Mean square is about the same as our attack type. Our F statistic is just a little bit higher than the attack type, but once again, our p-value is greater than our 0.05. So once again, it doesn't have any, significance in the variance against the anomaly score. So looking at that, really, honestly, what this table is telling us that, well, the packet length, no matter how much data is being transferred between the attacker and the destination, or the attack type, being DDoS or intrusion or malware, or even the severity level, low, medium, high, it really doesn't have an effect on what the anomaly score is on being randomized. About the ANOVA table, let's look at the second one with the ANOVA effect sizes. So remember again, the effect sizes provide insight on how much the anomaly score influences the packet length, attack type, severity level beyond just statistical significance. So these values help determine the magnitude of the effect. So let's look at the effect size metrics once again. So remember, eta squared measures the proportion of the variance explained by the independent variable. Once again, remember, is the anomaly score. Higher values indicate a stronger effect. Epsilon squared, well, that guy adjusts for small sample sizes, providing a more unbiased effect size estimate. Omega squared, that guy is a less biased estimate for the effect size used by a fixed factor or ANOVA. Omega squared, with the random effect, is similar to the other guy, but accounts for variability across different random samples. And then looking at the point estimate, this is the best estimate for effect size, and then we have our confidence level at 95%. The lower and the upper bounds indicate the range in which the true effect is likely to fall. So anyway, so we're looking at the packet length over here, right? So with the eta squared, we have the point estimate is 0.249. and the 95% confidence interval lowers is flat out 0, and then the upper is 0.012. Epsilon squared, we have the 0.004. And then looking at this guy, check this out. We have a negative 0.326, and the upper is also negative. Omega squared, which is our fixed effect, we have the point estimate of 0.004. We have a lower negative 0.326 and upper of 0.13310. Oh my goodness. And then we have the omega squared is completely different. There's no change whatsoever. And in fact, there's no change whatsoever for omega squared for all three of our different independent variables. So we can look at attack type, and then once again we can look at E squared. We have 0.241, kind of similar to the packet length. We have nothing for the lower, and then for upper we have 0.002. Espion squared, we have negative values just kind of like the packet length. And then for omega fixed, we have negative across the board. And then once again, omega squared random, we have nothing. Severity level, once again, omega ETA squared is 0.245, similar to the other guys. Nothing for lower. And for upper, we have 0.007. Epsilon squared is negative 0.001. Lower is negative 0.326. And for upper is negative 0.317. Omega squared fixed, negative across the board. And for omega random, nothing. What the heck does all of this mean? Well, the ETA squared values for the packet length, attack type, and severity levels are low. They all close to, 0.24 or 0.25, suggesting that the anomaly score does not really explain a large proportion of variance in these variables. The epsilon squared and the omega squared values are either negative or close to 0, indicating that little to no effect of anomaly score to these dependent variables. And since the confidence intervals, indicate negative or near 0 values, it suggests that the observed variance could be due to chance rather than meaningful effect. So our overall conclusion with this whole ANOVA test with this ginormous data set is the anomaly score does not meaningfully impact the packet length, attack type, or severity level based on these effector size results.
Okay, now that we've done all that, let's just do a few key takeaways of what we've done here. So first thing, let's talk about the purpose and importance. ANOVA helps compare means across multiple groups to determine if differences are statistically significant. When will we use it? Well, we'll use ANOVA when comparing 3 or more groups instead of just multiple t-tests, which reduces the risk of type 1 errors. We're also going to be using it for interpreting results of the p-value, or the sig. If the p is less than 0.05, then at least one group is significantly different. For S statistic, larger values suggest stronger evidence against the null hypothesis. And the effect size, well, eta squared and omega squared, shows how much variance is explained by group differences. So in real-world applications, ANOVA is used in cybersecurity, attack comparisons, medical research for drug effectiveness, or even marketing for customer behavior, and many more fields. Well, alright then, that concludes this presentation, and I hope you enjoyed it. So here are a few different research references that I used to compile this project, to include the cybersecurity data that I pulled from Kaggle, Investopedia to learn more about the ANOVA test, and finally data development video for learning how to do SPS in 15 minutes. Thank you very much, and I appreciate you watching.